Hi and welcome to video 4 of this topic on statistical inference. Today we're going to be talking about taking our work from last lesson. We're just looking at taking samples and the trends and building that to a deeper understanding of the normal random variable. This is Unit 4, Topic 3 for the Specialist Maths curriculum. So the idea is, what if we took two randomly chosen items from a population? Now we're going to be talking about sample means now. So we take two randomly chosen items. Now, if I take one chosen item, I'm expecting that one, my expectation is that it will be the mean. So again, I might just fall back to, and this does say normal random variables, but let's just can the normal for a second. Let's go back to that dice roll thing. So the mean on a dice roll is 3.5. I expect to get 3.5. I never will because 3.5 doesn't exist, but it's the middle. So when I take one dice roll, I expect to get 3.5. If I take another independently chosen dice roll, so not affected by the first, I expect to get 3.5 again. So the question is, what do I expect to get as an average of my two dice rolls? And that's what I'm saying here. Let x1 and x2 be randomly chosen items in the population. Then the sample mean, x hat, or so x bar, is equal to the first item plus the second item divided by 2. That's just a basic average calculation. Then the expected value of our sample mean is equal to the expected value of those two additions. So this sample mean is about taking the mean. Now that half doesn't affect my expected value. We can take a constant out, so the half moves to the front here, and an expected value of x1 plus the expected value of x2, and that's equal to half of mu plus mu, which is just equal to mu. So the expected value of my sample mean is equal to the average of the distribution, the expected value of the distribution. So again, if I've got a normal set of data, let's say here, and it's the heights of year 12 students, and it has a mean of 170 centimeters, and then some standard deviation, and I take, let's beef it up a little bit, I'll take a random sample of 3, 1, 2, 3, my expected value of the sample mean, which is those three, the mean of those three, add them up, divide by 3, is going to be the same as the expected value of the distribution, which is mu, the center. My expected value here is actually probably going to be more like maybe there. Okay, but it's a small sample, it's only 3. If I take a sample of 10, it will probably be more accurate. If I take a sample of 30, it will probably be more accurate. In fact, you can see that as we increase n, the sample size, the likeliness of my sample mean being close to the center improves dramatically. So what we should get is if we take a series of sample means, the first one might be here. If I'm taking a sample mean with 100 data points, the second one might be there. I'm expecting them all to be pretty good, because if I do get an outlier, it's going to be outweighed by the ones that are closer to the middle, and I'll get a lot of data right in the middle here. So as I increase my samples, I get a better understanding of the actual population mean. So that's the population mean, sample mean. The big thing here is that the expected value of our sample mean is just mu. And it's true for 2 samples, 3 samples, n samples. Now let's have a quick talk about our variance. Our variance of our sample mean, the variance of x bar, is equal to, and I'm just doing it for n equals 2 at the moment, is equal to the variance of, it's a mean, so it's x1 plus x2 over 2. And again, I can take that half at the front. Remember that variance of ax is equal to a squared times the variance of x, that rule from math methods. I'm doing that here. I'm taking the half at the front, but I'm squaring it. And I get the variance of x1 plus x2, which I can split up to be the variance of x1 plus the variance of x2. Now x1 and x2 are from the same samples, so they have the same variance, sigma squared plus sigma squared, with a quarter at the front, which gives me 2 sigma squared, which gives me sigma squared over 2. That gives me a standard deviation of sigma over the square root of 2. Now, what happens if we don't have 2? What happens if we've got a sample size of n? Well, we get the same expected value. The variance is now sigma squared over n, and the standard deviation is sigma over the square root of n. Now, if you don't quite follow the mathematics here, definitely ask, but hopefully you can see that with these values here, as I increase n, the expected value of my sample mean doesn't change, but the variance does. An increased n decreases the variance and decreases the standard deviation, which means that if I have an n of, say, 5, I'm expecting to get it could be really well spread out. Whereas if I have an n of 100, I'm expecting it to be a lot closer. And as I increase n, I get a more accurate estimation of my population mean from my sample mean, as you would expect. So let's talk about the distribution very quickly, just a summary. X is a random variable with mean mu and standard deviation of sigma. The sample mean has an expected value of mu and the standard deviation of sigma over the square root of n. And X is also normally distributed. Well, if X is normally distributed, then the sample mean is also normally distributed, which is an important assumption that we have to make. Let's have a quick talk about an example. A brand of rope is said to have a mean breaking strength of 50 kilograms with a standard deviation of 2 kilograms. So I might just make notes as I go. Mean, mu, equals 50, sigma equals 2. If a random sample of 50 ropes is selected, n equals 50, and tested for breaking strength, determine the mean and standard deviation for breaking strength of the sample to 2 decimal places. What is the probability that the sample of 50 ropes has an average breaking strength of that? What is the probability 20 ropes has an average breaking strength of more than that? Blah, blah, blah. So I've highlighted the 20 there just to make sure that people don't see it or miss the fact that it's different. So we know that the expected value of x bar, is equal to mu, which in this case is equal to 50. So that's pretty easy. And we're asked to find the standard deviation. The standard deviation of x bar is equal to sigma over the square root of n, which in this case is just 2 over the square root of 50. Now the square root of 50 can be written as 5 root 2. So I could write this down as 2 root 2 over 10, or root 2 over 5. So that's my standard deviation. Whatever that's equal to, you can work out the exact value, although it does say to decimal places, so I probably should work out the exact value. Square root of 2 divided by 5 is equal to 0.283, but 2 decimal places, 0.28. Okay, so that's my standard deviation. Now, what is the probability that the sample of 50 ropes has an average breaking strength of more than 50.5? It's a mass, so it's a continuous variable. So this is kind of our A, and this is kind of our B. I might do it over on the side so we can still see the question. So B, the probability that the sample has an average of over 50.5. Well, this is a normal distribution, so we're doing a norm CD on our calculator. I want our lower bound, I want it to be greater than 50.5, so I want our lower bound to be 50.5. I want our upper bound to be infinity, which for me, just looking at the standard deviation, etc., I'll just make it probably 100 will be fine. I want my standard deviation to be root 2 over 5, and I want my mean to be 50. And so I put that into my calculator, which I'll do on here, but you'll have to just bear with me as my calculator starts. Okay, and I'll just change the size here. So I'm going to go into run matrix, and I'm going to go into options. Sorry, I should have went into stats, distribution, normal CD, and in here I want 50.5 as my lower bound. I'm going to make 100 my upper bound. My standard deviation is root 2, and I have to just make sure I'm outside the square root sign, divided by 5, and then my mean is 50. Now this should be a little bit less than 50%. And it's quite a bit less, but actually when I think about my standard deviation was 0.28. So this is almost 2 standard deviations away. So 0.385 is the probability. 0.0385. And it's pretty low, but you can see if I change my sample size from 50 ropes to 20 ropes, well, the n changes, which means my standard deviation actually increases a bit, which means my probability will increase that it's greater than 50. So the point here is, if you're a company that's testing the breaking strength of your rope, taking a larger sample decreases your standard deviation, which increases the accuracy of your probability, and lowers the width of your confidence intervals, which we'll get to next. So the standard deviation for this new one will be over root 20. So this is part C. The probability that x bar is greater than 50.5 is going to also be equal to a normal CD calculation. But in this case, I've got 50.5 up to infinity, which I'll do as 100. And then in this case, I've got sigma, which was originally 2, but over root 20. And I could simplify that, but for this benefit of this, I won't bother. And so I go back to here. The only thing that's changed is sigma. So I'm going to go back into here. This can save you some time. I've got all this other stuff already here. So I'm just going to delete that and make it 2. And I'm going to delete that and make it the square root of 20. Execute, and I've got 0.132. And that's equal to 0.132, which is about 4 times bigger than this. So we've got a 4 times increase in probability. Now, there's no relationship between probability and sample size in terms of multiple increases, but that's the case here, and that's a comment you can make. The question then says discuss, and hopefully you can see from this example that as we increase our n, our sample size, our probabilities, well, basically our standard deviation comes in, it compresses the normal distribution, which means that our probability of being outside that range or inside or whatever will change, creating more accuracy in our estimations. So that's 15D. There's the questions you can do from 15D. All the best.